and get that going. All right. This, I'm going to reference the book. And so today we are actually now starting the book. The first chapter, chapter one is about functions. Now the first chapter, the author isn't doing any real deep dives into any particular topic. He's just like doing a quick survey of things that you should have already come across about functions. So if there's anything here that seems a little bit awkward, this is the author giving you your chance to identify where you're already weak and you need to go fill in that gap. So if there's a particular type of function that comes up that you have a gap on, then maybe go find some YouTube videos in between today and tomorrow to try and start filling in those gaps, get comfortable with those types of functions. With the exception of the trig functions. We'll do some more on the trig functions later, but any of the other functions that we cover here today, if it's throwing you off in some way, that's a good sign that you need to go back and start filling in that gap. Now obviously I can't give as much detail as the author gives in 1.1, so 1.1 would have been a great section for you to read. Get a survey on all these functions. So that's what we'll start with, 1.1. We're trying to do 1.1 and 1.2 today, so let's get going. Let me go past this line without moving the camera. Okay, so we talked a lot about functions last week. I wanted to introduce you functions to the way that I think you should define functions, but now I'm going to just be consistent with the book, even though I don't like it. So how does the author define a function? A function, f, from a set D to a set Y, is a rule that assigns a unique element, f of x in Y, to each element x in D. What can I do for you?
Are you missing any people?
Nope.
Thank you.
Very welcome. So let's say that one more time. A function f from a set D to a set Y is a rule that assigns a unique element f of x in Y to each element x in D. So for every x in D, we assign a unique element to it, f of x, which has to be in Y. And the author goes through a bunch of intuitive functions that we might talk about in our day-to-day life. So one of the functions he talks about is the boiling point of water relative to elevation. Given your elevation, there's a certain boiling point for water. The higher your elevation, the lower the boiling point for water, because there's less atmospheric pressure. So that would be a function. Your x's would be your elevation. Your f of x's would be the boiling point of water. Given x, you know f of x. It's mapping a bunch of elevations to a bunch of boiling points of water. Typical kind of function. Okay, we call this D, where all the x's are, all your inputs, the set of all your inputs, that D we call the domain, and we call all the f of x's that you use in Y the range. Now Y is not your range. All the f of x's that you use in Y are your range. Does that make sense?
Yeah.
You don't have to, your function doesn't have to use all of Y. It has to use all of D. So if I have a function, here's my set D, and we have 1 and 2 in it, and here's my set Y, and we have 3 and 4, and my function assigns 1 to 3 and 2 to 3, it's a function. We assigned everything in D to something in Y, and we did it uniquely. 1 only goes to one thing, 2 only goes to one thing. Make sense? The range of this function is the set containing 3. It's not the set containing 3 and 4. So the domain is the set 1, 2, but the range is just 3. Make sense? Okay. Wonderful. So then if we have y equals f of x, so y is some function in terms of x, we call x the independent variable, and we call y the dependent variable. Now these make intuitive sense. Given x, you can figure out y. Going back to our elevation boiling point of water example, given my elevation, I can figure out the boiling point of water. The boiling point of water is a function of my elevation. The boiling point of water depends on what the elevation is. It's the dependent variable. What's y? It depends on what your x is. If you give me an x, I can tell you what the y is. Y depends on x. X is your independent variable. It's the one you're plugging in. Make sense? Okay. No. when we define a function y equals f of x and don't state the domain, then we assume the domain to be the set of all the real numbers where f of x is also a real number. We call this the natural domain. So we're not going to always specifically state what the domain is. If we do not specifically state what the domain is, you're basically assuming it's all the numbers that you can think of that you can plug into the function. It's called the natural domain. It's what we just assumed. So let's do some examples here with these functions. And you're going to tell me for each of them what the domain is and then what the range is. And since the domain isn't explicitly stated, we're going to assume natural domain. So let's look at the function y equals x squared. That's the function we're looking at. What is the domain? What are all the numbers I can plug into that function and still get a number out?
All the numbers.
Every number. So I could use our r here to mean all real numbers, or I could use interval notation, which says all the numbers from negative infinity to infinity. All the numbers. Good? Okay. What's the range of this? What are all the outputs I get out of this function?
0 to infinity, including 0.
So we can get 0 out of this. Notice if I plug in 0 for x, what's y?
0.
0. So 0 comes out. Can we get positive numbers? What do I get if I plug 2 into this?
4.
4 comes out. What do I get if I plug negative 2 into this?
4 as well.
4 again. Is there any number I can plug in for x that makes y negative?
Not any of them.
No. Because a positive times a positive gives me a positive number, and a negative times a negative gives me a positive number. So all the outputs, all the y's that work for this function, they start at 0, including 0, and then we have all the numbers after 0. Interval notation. Start at all the numbers from 0 to infinity, including 0. This is saying all the numbers from negative infinity to infinity, not including negative infinity, and not including infinity, because you can't include those because they're not real numbers. Okay, so let's look at everyone good with this example. Any questions on this example? Okay, next, y equals 1 over x. Now, in general, when we're thinking about what are all the numbers we can plug into the function, there's pretty much only 2 things we have to watch out for. There's 2 rules that we can't break when we're working with real numbers. Number 1, we can't divide by 0. Number 2, we can't take the square root of
2.
We can take the square root of 2. That's real easy. It's just the square root of 2.
A negative number.
We can't take square roots of negative numbers, right? So those are the only 2 things we really have to watch out for here. Outside that, we're pretty much good. So what are all the numbers I can plug into this function? What are all the numbers I can plug in for x?
Negative infinity to infinity, not including 0.
Every number but 0, right? We can divide by negative numbers, that's fine. We can divide by positive numbers, that's fine. The only thing we can't divide by is 0. So this is negative infinity to 0, not including 0, union with 0 to infinity. Union those 2 sets together. Basically everything except 0. So all the negative numbers up to but not including 0, and then all the numbers greater than 0, not including 0. Is that too small?
Yeah.
I could write that a little bit bigger.
How is it? Yeah, I'm confused why how it communicates non-zero.
Square bracket means include it, round bracket means don't include it. So negative infinity to 0, round means not including 0. So negative 0.1's in there, negative 0.001's in there, negative 0.00001's in there, but not 0. Union with, again, round bracket, not including 0, all the way up to infinity. If we want to include 0, we put the square bracket. That means include 0.
Oh.
So when you see notation like this, if I do x comma y, not as a point, but as a, let me not use x comma y because we're talking about an interval. If I say all the numbers from x1 comma x2, and I'm talking about an interval now, not a point. We have the same notation. It's not great notation, but understood as an interval. This is a set of all x such that x is greater than x of 1, and x is less than x of 2. If I were to put a bracket here, then that would mean greater than or equal to x of 1. If I were to put a bracket here, that means less than or equal to x of 2. That's how that notation works. Okay.
Did we go over like union notation and whatnot last week?
we not talk about unions of sets?
I don't think.
It's in my notes. Skipped over the set notation. When you union two sets together, you just take all the elements of both and put them into one set. So if I have two sets, if I have the set A and the set B, so A is a set of objects, B is a set of objects, then A union B is equal to the set of all X, where X is in A or X is in B. So if I have the set 1, 2, 3, unioned with the set 3, 4, this is just equal to the set 1, 2, 3, 4. Unioning sets just takes all the elements that are in here or in here and puts them all in one set. They just include everything in both sets. Okay. So this is saying every number except 0. All the negative numbers up to 0, but not including 0, and then all the positive numbers down to 0, not including 0. Good? Okay. Now, what about the image of this thing? Well, sorry, what do we call it? Range. What about the range of this thing? What are all the values we can get out of there?
Wouldn't it just be the rationals?
Just the rationals? No, 1 over square root of 2 is not rational. I can get that out.
I imagine everything is what things go in there, other than 0. No, sorry.
Can I ever get 0 out of there?
You can't go above 1.
Huh?
You can't get 0.
I can't get 0. 0 is the only thing I can't get out of there.
Yes.
You can't plug in 0. Okay, so you're plugging in X to get Y?
So we already talked about all the x's I can plug in. I can plug in anything but 0 and we're fine. If I plug in 0, we're dividing by 0, that doesn't work. Now what are all the outputs I get?
The interval from
It's the exact same thing. It's negative infinity, 0, union, 0, comma, infinity. If we graph what this thing looks like real quickly, 1 over x, it looks roughly like this.
But you can't get whole numbers, can you, other than 1? So you can't get 2.
I can get any whole number. 2 divided by a half. 1 divided by 1/2 gives me 2.
Okay.
For any y you want to get, just divide by the reciprocal. And every number has a reciprocal. If I want to get 13 out for y, just plug in 1 over 13 for my x. And 13 comes out. Alright, 1 over 1 over 13 is the same thing as 13. Make sense? Okay.
Oh, I got you.
Okay, so we can get anything but 0 out. Because how do we get 0? Well, we need to divide by 0's reciprocal, which you can't do. Because the reciprocal of 0 is undefined. Okay, so now let's look at the square root function. Y equals the square root of x. What are all the values we can plug into that function?
All the positive numbers.
All the positive numbers, what about 0? Can you take the square root of 0?
Yeah.
What times y equals 0? 0.
So it's good.
0 times 0 equals 0. So 0 is 0 square root. So we can plug in 0 to infinity, including 0. Can't plug in negative 1. I can't take two real numbers, multiply them together, and get a negative number out. Right?
Yeah.
Okay. So that's what we can plug in. What can we get out of this function? What are all the possible outputs?
The same thing.
The same thing. We can't take the square root of something and get a negative number. So we can't take square roots of negative numbers, and we can't take the square root and get a negative number.
So that's the principal square root then?
So we're talking about the square root function. We're not talking about x to the 1/2.
Oh, okay.
Okay, next. What is the domain of this function? Square root of 4 minus x.
Negative infinity to 4.
Negative infinity to 4.
Yeah, I like that.
Everyone Want to see how she got that so quick?
Yeah.
Negative infinity to 4. Do we include the 4?
Yeah.
Yes.
Yes. So look at what happens when we plug in a number not in this interval. So try plugging 5 into that function. If I plug in 5 for x, what do I get?
Negative 1.
Square root of negative 1. What's the square root of negative 1? Not a real number. Can't do it. Right? But plug in negative 10 now. What's negative negative 10? It's just positive 10. 4 plus 10, 14, square root of 14. Yeah, we can do that. We can take the square root of any positive number, and we can take the square root of 0. Just can't do it with negative numbers. Perfect. Okay, what's the range on this one?
Shouldn't be the same as last.
Would it just be from like 0 to infinity?
Here's a good question to ask sometimes if you're getting stuck. What's the biggest number I can get out of this, and what's the smallest number I can get out of this?
0 and infinity.
0 and infinity? Okay.
No,
Everyone see that?
yeah.
Plugging in 4 gives you 0, and then plugging in negative infinity gives you positive infinity.
Yeah.
Okay, finally the last one. What's the domain of that function?
Negative infinity to infinity.
I can plug in everything?
Yes.
Yeah.
Try plugging in 2. Tell me what you get.
Minus 3.
Square root of minus 3. And you can't take the square root of minus 3 and get a real number.
So no positives.
Well,
And
you can
put
put
in
in 1.
What do you get if I plug in 1?
0.
What's the square root of 0?
0.
So
It's
negative
Negative infinity to 1.
Negative infinity to 1. Okay, try plugging negative 2 into that. What's negative 2 squared? Negative 2 times negative 2. That's positive 4. 1 minus 4, negative 3. Square root of negative 3. Oh, it doesn't work.
So it's just negative 1 to 1.
Negative 1 to 1. Those are all the numbers we can plug in. Good? If I try plugging in a smaller negative, like negative 2, we break it. If I try plugging in a number bigger than 1, we break it. If anything between negative 1, look, I can't let x squared become bigger than 1. When is x squared less than or equal to 1? On that interval. If we were to graph the function x squared, here's negative 1, here's 1, here's 1. If we graph x squared, then it looks roughly like this, right? A parabola.
Yeah.
The only place where the domain of that function is less than 1 is right here. Where it's below the line, that's between negative 1 and 1. So we need x squared to be less than or equal to 1, because if x squared gets bigger than 1, then we're going to we're going to subtract something that's more than 1 and get a negative number. That make sense? Am I overstressing it? Okay. So what's our range here then?
Just 0 to 1.
Just 0 to 1? Who agrees with that?
Yeah.
Yeah, Jeremy does? Including 1?
Yes.
Yeah.
Okay. How do I get 1 out of that function? What do I plug in to get 1? 0. Make sense?
How do you get 0 though?
How do you get 0? Plug in 1 or negative 1.
Oh right, 1 is 0 squared, right?
So when you plug in 0, you maximize the function. As you plug in numbers closer to 1 or negative 1, then the function becomes less and less. Okay.
I'm just not sure how you get 1 as an output.
Plug in 0. 1 minus 0 squared.
Yep.
Yep. Wonderful. Okay, so that finishes those examples. Moving on. If f is a function on D, D being the domain, the set of all possible inputs, if f is a function on D, then the graph of f is a set of points x comma y, or x comma f of x, for all x in D, in the Cartesian plane. We already talked about this last time. It's just a graph of a function, exactly how you think about it. Think about all the numbers that satisfy the equation as points on the plane, and then you get a function. So let's do some of these, even though I just barely did it. We'll do it again. So let's graph y equals x squared on the domain -2 to 2. So we're only going to use from here to here. That's the only domain we're going to use. And we're going to graph this function, y equals x squared. So how do we do that? Well, going back to your junior high days, you probably did something like this: a column with your x's and a column with your y's, right? And you said, if I plug -2 in for x, what do I get for y? 4. If I plug in -1 for x, what do I get for y?
1.
Plug in 0. Plug in 1. Plug in 2.
4.
And then so you might come over and plot these points. So you might go 0, 0's here, 1, 1's here, 2, 4's here, -1, 1's here, -2, 4's here. Everyone with me on everything we've done so far?
Yeah.
Okay, and then you did something absolutely crazy. You said, so it looks like, and you just went ahead and gave a nice curve to all of that. And how did you know that it curved between these? How did you know it doesn't just go a straight line like that, a straight line like that, a straight line like that, and a straight line like that? Or how do you know that the function didn't go like this in between? And it was all squiggly, and you happened to hit points on there. How did you know that it was just a nice solid curve like what you thought? You can say, oh, well, just plug in more points, but then how do you know what happens in between those points?
It keeps happening.
And you can plug in more points, and you can say, how do you know what happens in between those points? It does, in fact, look like what your teachers told you from the beginning. It's just a parabola. It does have a nice curve like that. But how on earth do we justify that? We will finally be able to do that in this class, calculus. We'll be able to justify it with some calculus. But not going to justify it right now. But it is a nice, beautiful curve that you know. Huh?
So we prove why that works.
We'll show that how you think about a parabola is what a parabola is, yes. But we only go from 0 to 2, so we actually need to stop the function here. We can't go beyond that, because this is our whole domain. So cut it short. But it is just a nice parabola, but cut short. Don't draw it past 2 and -2. Okay, so graphing a function. Now we have a way of testing whether some graph is actually a function, and we call it the vertical line test. And already seen this test, I'm sure, but we'll go over it anyways. So let's look at some equation like y squared plus x squared equals 1, and let's graph this thing really quick. All right? So if I plug in 0 for x, what do I get for y?
Y equals 1 and then 1.
So let's do it real quick. If I plug in 0 for x, then we have y squared plus 0 squared is equal to 1. You with me? So maybe you make my t-chart down here for a second. So we're doing our t-chart. We're doing x's and y's. We're plugging in 0, seeing what we get. So plugged in a 0 for x, 0 for x. So I get y squared is equal to 1. Maybe I'll write that. Y squared is equal to 1. You with me? So now I need to square root both sides, so I get y is equal to plus or minus the square root of 1, which is equal to plus or minus 1. Right?
Yep.
Notice that these are the two solutions to this equation. If y is equal to -1, what's -1 squared?
1.
If y is equal to +1, what's +1 squared?
1.
So those are the two solutions. So if x is 0, y is 1 or -1. So let's graph that. So when x is 0, that's when we're on, right here is where x is 0. Then we have a point at 0, -1, and a point at 0, 1. Those are those points, right? Okay, let's do our chart a little bit backwards. What about when y is 0, what's x? So let's figure that one out. Maybe you can already see it. If I plug in 0 for y, what does x have to be?
1 minus 1.
Plus or minus 1. So 1, -1. So let's plot those points. Right? And you can continue plotting points on this and be really careful, and you can see when it's all said and done that what you get is a circle with radius 1. So chances are you've already seen the equation. They probably wrote it. X squared plus y squared is equal to r squared, something like that. Gives you the equation of a circle with radius r. Anyways, so here is our graph of this thing. There's a graph. Is that thing a function?
No.
No, it's not a function. When I had one input, I got two outputs. No, not a function. The vertical line test is a way that we can tell whether it's a function just from looking at it. What the vertical line test is draw a vertical line through any point of your graph. If it intersects it at more than one point, then it's not a function. In other words, if you can find some x that gives out two y's, it's not a function. Vertical line test. So you should be able to now know right off the boat if this is a function. Is that a function? No, vertical line test. That intersects more than one point. Not a function. But if I were to do the graph of something like this, now it is, right? No, not a function still. But if I get rid of the bad part, now, yes, it is a function. Vertical line test. So just from looking at the graph, just a picture of the graph can communicate a lot of information about the thing you're talking about. One thing, namely whether or not it's a function, vertical line test. Any questions there?
Y is always considered the range.
The range is a set of all y's that you can get out of the function.
Is that right? So I'm saying we always make Y the output.
It's convention,
Okay.
but no, it's not always the case.
So sometimes you might have to do the horizontal test.
But yeah, there could be scenarios where that happens. Okay.
Ah. Remedial math, huh?
Yes, sir. Okay. Next, another way that we talk about functions, another way we define functions is what we call a piecewise definition of a function. Maybe the function we're trying to talk about, we can't come up with just one equation that talks about it in a nice way. I mean, when I draw some picture like this thing, so I have it come down like this, go up like this, and then over. Is that a function?
Yeah.
Yes.
Yeah, but if we try to find just one equation to represent that thing, good luck. It might make more sense to try and break this thing up into three pieces. Say, okay, we'll use an equation for this part, an equation for this part, and an equation for this part. So scenarios like that, it's nice to have a piecewise function. Or the example we're right about to do, absolute value. So a function, when we graph absolute value, it looks like this, and then like this. Might be hard to find just one function that does that than that, but if we look at that piece, that's easy to define. If we look at that piece, that's easy to define. So don't make life hard for yourself. If you got some weird function that you're trying to come up with, don't think you got to do it all in one equation. You can use several equations. Use as many as you want. Keep it easy. So the definition of absolute value, hopefully we already are familiar with absolute value. Real quick, what's absolute value of 2? 2. What's absolute value of negative 3? 3. Okay, you got it. So our definition for absolute value of x then would be, it's equal to x, it's equal to whatever you input, if that thing's greater than or equal to 0. And it's equal to the negative of whatever you input, if that thing's less than 0. So the absolute value, we'll just start right here for a second, the absolute value of negative 2, looking at this definition. So when I plug in negative 2 for my x, is negative 2 less than 0? Then we spit out negative of what we put in. So it's equal to negative 2. And negative 2 is the same thing as 2. Okay. So let's look at another example. F of x is equal to, here's my piecewise function. It's equal to negative x when we plug in a negative number. It's equal to x squared when we plug in a number between 0 and 1. And it's equal to 1 when we plug in a number greater than 1. Let's graph this thing. So first thing we do is we look at all the negative numbers. I'm supposed to use the function negative x. Do we know what the graph of negative x looks like? What does it look like? just sloping down, a line with a slope of -1. So that's going to look like this, if I could draw half decent. Now, it's up to but not including 0. So far we don't include the origin. So we put an open circle there to say we don't include the origin. And it's just this part. So I've taken care of this piece of the graph. With me?
Mm-hmm.
Now I need to take care of this piece of the graph. So from 0 to 1, I need to graph x squared. So now we include the origin. So now I can get rid of that open circle. Because when I plug in 0, we just get 0. So 0, 0 is on there. But 0 to 1, we have x squared. So from 0 to 1, it's a little piece of a parabola curving up like that. Sorry if it's hard to see. Should have spaced that out more. With me?
Mm-hmm.
Now we say circle dot because we include the point 1, 1. Now, if we plug in numbers greater than 1, we just graph 1. So that means 10 goes to just 1. 5 goes to just 1. Pi goes to just 1. Everything goes to just 1 if it's greater than 1. So that is this line. So we just graph the function. Make sense?
Yep.
And it's basically the same thing as just graphing 3 functions, but only a piece of each of those 3 functions. Cool. So now we got 2 functions. These 2 you might not have seen before, but they're really, really simple. We got the floor function and the ceiling function. The floor function just means whatever your x is, round it down. Doesn't matter if it's 0.9, always round down, round the decimal down. The ceiling function means always round up. So let's look at the floor function for a second. 2.4, rounded down, what do you get? 2. 2.9, rounded down, what do you get? 2. 0, rounded down, what do you get?
0, 0.
0. Negative 0.03, rounded down, what do you get?
0, 0.
Negative 1, rounded down, not up. Round down. What's smaller, negative 1 or 0?
Negative 1.
Negative 1, we round down. Okay. Floor of negative 2, what do we get?
Negative 2.
Negative 2. Floor of negative 1.7, what do we get?
Negative 2.
Negative 2. Wonderful. Okay, now let's do the same thing but ceiling. Ceiling of 2.4, what do we get? 3. Ceiling of 2. Write this out. 3. I don't need to write these out, you can just tell me. Ceiling of 2.9, what do we get? 3. Ceiling of 0, what do we get? 0. Ceiling of negative 0.03? 0. Ceiling of negative 2? Ceiling of negative 1.7? Negative 1. All right, think you got it?
Yep.
Okay, intervals. We already talked about intervals. I should have put that note earlier. I just noticed that. Intervals are just things of the form. They could look like this, x1 to x2. It could look like x1 to x2. It could look like x1 to x2, and then square brackets on both sides. Those are the 4 types of intervals we can have. These are all the numbers between x1 and x2, not including the endpoints. All the numbers between them, including x1. All the numbers between them, including x2. And if I would have done this, then it's all the numbers between them, including x1 and x2. Those are the 4 intervals. Okay, so move the camera now. Yes, otherwise I will forget. Okay, now I need to move the camera when I get on the whiteboard. So, squiggly, 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 squiggly. Okay, what were we talking about? This thing, yeah, whatever it is. Let f be a function defined on an interval I. So I some interval, just some contiguous set of points, maybe including the endpoints, maybe not, we don't know. And let x1 and x2 be any 2 points in the interval. So my interval, some set of points, x1 and x2 are somewhere inside that interval. if x1, we'll just use your intuition first and then we'll come back and read the definition. What do you expect an increasing function to do?
Keep going.
Keep going. Yeah.
Question, is this function increasing or decreasing?
Decreasing.
Decreasing. What about this function? Is this function increasing or decreasing?
Increasing.
Increasing. Okay, so you already have the intuition. We're going to define these things now, and it's going to say exactly what your intuition thinks it should say. So we say that if x1 is less than x2, so which one are we going to do first?
Increasing.
Increasing. Okay. Oops, I'm erasing the increasing one. So let's throw up what you expect an increasing function to look like really quick here. Okay, there's increasing. Now we're saying that if x1 comes before x2, so here's x1, here's x2. Doesn't matter where. x1 is just somewhere before x2 in the domain of the function. If x1 comes before x2, then f of x1 is right here. It's the height of this point. And f of x2 is right here. That's the height of this point. If x1 comes before x2, then f of x1 has to be less than f of x2. If that's the case, if x1 coming before x2 implies f of x1 is less than f of x2, then the function's increasing. Make sense?
Yep.
Now let's look at it the other way.
And x1 always has to be less than, or
If x1 is less than x2.
what I'm saying is x1 always has to be, I don't know how to describe it.
On the left-hand side of x2?
Sure, but on the,
No, only if it's less than. We could have also said, if x2 is less than x1, then swap it over here. So call the smaller of these two numbers, call the smaller of the two things you pull out of here x1. Set it up so that this is the case. But the intuition is exactly what you think. So now let's do a decreasing function. So here's a decreasing function now. So here's x1, here's x2, f of x1 is the height of this point, here's f of x1, and f of x2 is the height of this point, here's f of x2. Now, if f of x1 is less than x2, implies f of x1 is greater than f of x2, then the function's decreasing. Go ahead.
That says if x1 is less than x2.
Right.
Why is the function greater than?
Look at this function that we have. It's decreasing, right?
Yeah.
Here's my point x1. It's on the x-axis. Here's my point x2. It's on the x-axis. This is like -3 and that's like 1.
Okay.
So we have -3 is less than 1, or x1 is less than x2. Is that the case?
Yeah.
Okay. What's f of x1? What is the height of the function at x1? That's the height of this point. That's like 3. What's the height of the function at x2? It's like -1. So f of x1 is right here, f of x2 is right here. So f of x1 is greater than f of x2.
But you're saying the exact same thing as the first one, except the implication is flipped.
No.
Yeah, that's what's flipped. But
Right, the greater than or less than sign. If f of x2 was greater than f of x1, the function would be increasing. Look, if as my x gets bigger, my y gets bigger, my x is increasing. If as my x gets bigger, my y gets smaller, my function's decreasing. Let's try it another way. Maybe if we use y1 and y2. And it'll just be less messy. y1 is less than y2. y1 is greater than y2. Okay. So we got two types of functions that we've got here. Start with the increasing function. So some increasing function. Now pick any point in the domain you want, call it x1. Doesn't matter. Now pick any point after that point in the domain, call it x2. So some point later, x2. The only rule, x2 needs to come after x1. That's one rule.
Okay.
So x2 is later in the function than x1. If the function's increasing, then we expect the height at x2 to be higher than at x1.
Yeah.
If the function is decreasing, then we expect the height at x2 to be lower than at x1.
Okay.
That's all we're checking.
Okay.
So we probably should have left this. So f of x1, f of x2, that's 1, f of x1, f of x2. Okay, increasing and decreasing functions. Next. A function y equal to f of x is an even function of x if f of negative x is the same thing as x. F of x. As f of x. If it doesn't matter whether or not you plug in a negative number or the positive number, you get the same thing, the function's even. So plugging in positive and negatives gives you the same output, the function's even. Odd function of x if f of negative x is equal to negative f of x. If plugging in a negative gives you the same output, but negative. So let's scribble somewhere where the camera can see for a second. We'll just scribble down here for a second. So really quick, look at a function like this. If I can, well, we'll just use a nice simple one. So a function like this is a function where, pretend that this is symmetrical, where if I plug in a negative value or a positive value, that is just really not symmetrical, my picture's gonna lie. Let me be a little bit more careful here. Okay. Still terrible. Okay, so here, pick some x. Here's x, here's its height. Notice that negative x has the exact same height. That's what we mean by an even function. Both x and negative x give you the exact same height. Now don't get confused by the side that we chose. Once again, let's say at this side's x. Here's the height at x. What's the negative of this number? It's right here. If x is -2, then negative 2 is right there. Still gives the same thing. So for any x you pick, plug in as negative, you get the exact same output. Then the function's even. Even functions are symmetric about the y-axis. With me?
Yeah.
Okay, now let's look at an odd function. So, odd function is something like this. That's terrible. Odd functions are symmetric with respect to the origin. If we draw a line like that and reflect it, then we're going to get the exact same thing. But what an odd function does is, whatever x gives me, so if this is my x, plug in the height, that's what I get for x, right?
Yeah.
Then negative x gives me the exact same height, but in the opposite direction. So if right here I get a height of 10, then at that point I get a height of -10.
That makes it odd.
And that's called an odd function. So odd functions have symmetry with respect to the origin. If you reflect this across the origin, you land in the same place. Even functions have symmetry with respect to the y-axis. Go ahead.
Do all functions have to be even or odd?
Nope.
So it's just these
A function
cases.
can be, yep. And a function can also be even and, well, can a function be even and odd? I think it can.
Do you have an example for one?
I was about to say a circle, but that's not a function. I don't know, I don't have one off the top of my head. But let's keep going. So now let's test some functions and see if they're even or odd, or both or neither. So let's look at f of x equals x squared. Now, you say it's even because you know it's going to be symmetric, but let's actually run it through the test. Notice that f of negative x is equal to negative x squared. You with me on that? Which is the same thing as x squared. I can factor out the negative 1. Negative 1 squared is still just 1. Which is f of x. So f of negative x is equal to f of x. So it's even. You follow that?
Yeah.
Now notice that f of negative x is equal to, we just barely did it, x squared. But negative f of x, what's negative f of x equal to? Negative x squared,
Yes.
right? Is x squared and negative x squared the same thing?
No.
No.
No. So f of negative x and negative f of x are not the same thing. So it's not odd. It was even, these were equal. It was not odd because these were not equal. Make sense?
Yep.
So this first one we had even, not odd. So this one was even, not odd. Okay, let's test this one. So does adding 1 to it change anything? Let's see. So now what is f of negative x equal to? That's still just negative x squared plus 1, right? We're just plugging in negative x everywhere we see an x. What's negative x squared?
Just x squared.
Same thing as x squared, and we still have plus 1.
So it's still be even?
So it's still even. You follow that?
Yep. Yeah.
But now let's look at negative f of x. What does that equal to? That equals negative, maybe we'll do this in a couple steps, negative, so we're saying negative x squared plus 1, negative f of x, you with me still? Now distribute the negative, this is equal to negative x squared minus 1. Is that the same thing as that?
Nope.
Nope.
Not even close, so it's not odd. So still even, not odd. Okay, let's look at f of x is equal to x now. We know what that function looks like. So just based off of what we know from what this function looks like, already tell me, is it even?
It's not.
No. Is it odd?
Yes.
Yes.
Yep.
Okay, so your intuition, just thinking about symmetric with respect to the y-axis and symmetric with the origin, guided you well. Now let's really quick run through it. What is f of negative x?
Just negative x.
Negative x, is negative x the same thing as f of x? Or the same thing as x?
Nope.
No, so not even. Okay, let's look at negative f of x. What does that equal to?
Negative parentheses x.
Negative x.
Yeah.
So notice f of negative x and negative f of x gave you the same thing. So it is odd, just as we expected. Right?
Okay.
So not even, the odd. Okay, let's look at x plus 1. X plus 1, first let's check if it's even. So what is f of negative x equal to?
Negative x. Plus
See?
1.
Negative x plus 1. Is that equal to x plus 1?
Nope.
So it's not even. So not even. Now let's check negative f of x. Can't write right here. Negative f of x. What does negative f of x equal?
Negative x subtract 1.
Negative x plus 1, let's make sure we spell the algebra here so we don't get lost, is the same thing as negative x minus 1, right? Is negative x minus 1 and negative x plus 1 the same thing?
Nope.
No, so it's not odd. So notice something a little bit curious. When we had an even function and we added 1 to it, it was still even. But when we had an odd function and added 1 to it, it wasn't still odd.
Because it wasn't going through the origin.
Right, because it wasn't going through the origin anymore. Okay, so there's some examples of that. Now some basic types of functions. I didn't think we needed to review lines in this class. Do you guys remember the equation y equals mx plus b?
Yeah.
That one still? Okay, so I don't want to rederive all that if we don't need to. So y equals mx plus b, or f of x equals mx plus b, same exact thing. This is the equation of a line. We call this a linear equation, or a linear function. A function whose graph just looks like a line. Now b and m are constants. These are not variables. X is the only variable. M we call the slope, and b we call the y-intercept. Wonderful. Do we need to see where these come from, or is it still?
It's coming back.
You got it? Because we can rederive these things pretty quick. It just take an extra 10 minutes. So if we need to do more in lines, we can go ahead and do them and make sense why that's the slope and why that's the y-intercept. Anyways, so let's look at a particular one of these functions and make sure we remember how to graph them. So this is what they look like in general. A particular one would be f of x, or y equals 2x plus 3. What does something like that look like? Well, that's a function that goes through the y-axis at 3. B's our y-intercept, right? And it has a slope of 2. So if you go over 1, you have to go up 2. So if I go over 1, I have to go up 2. Or if I go back 1, I have to go down 2. So it looks roughly like this thing, right? Terrible at drawing, but there's our rough line. You see it?
Yeah.
Okay, let's do another one real quick. What if I did something like y is equal to negative 1/2, not 1 over x, negative 1/2 x minus 3. What does that look like?
2 over 1 up, and then intersecting on -3.
So our intersection is -3, so we know that this is a point on it. Then we have to go over 2 to go up 1, down 1, negative slope. So this has to be a decreasing function. If the slope's positive, it increases as we go. If the slope's negative, it decreases as we go. So if we go over 2, we go down 1. If we go back 2, then we go up 1. And so it looks roughly like that thing.
Yeah.
Good? So there's a couple of those linear functions. Now let's look at identity function. An identity function spits out whatever you put in. So identity function f of x is just equal to x. If you put in 3, you get out 3. If you put in 6, you get out 6. What does the graph of that look like? Just a nice line like this right through the origin. Although I didn't draw a nice line, right? If you plug in 3, you get out 3. If you plug in -3, you get out -3. Whatever you plug in is what you get out. Identity function. Good? Okay. Now let's look at a function like y equals 3. What does a function like that look like? If x is 0, what's y?
3.
If x is -2, what's y?
3.
If x is 200, what's y?
3.
So when x was 0, we got y is 3. When x is 1, we got y is 3. When x is 2, we got y is 3. When x is whatever, we've got y is 3. No matter what x is, we get y is equal to 3. It's a constant function. Good?
Yeah.
Okay, so notice all those functions are linear functions. These are both linear functions, they're just special types of linear functions. This is the type of function you get when m is 1 and b is 0. This is a special type of function you get when m is 0. If m is 0, then we just have a constant function. But they're all linear functions, they all just give you lines. Good?
Yeah.
Okay. Now, two variables, x and y, are proportional if one is always a constant multiple of the other. That is, y is equal to some constant times x for some non-zero constant k. It's proportional. You increase one, you increase the other, if you increase one, you increase the other. If you decrease one, you decrease the other. What's an example of a function that has a proportional relationship in our day-to-day lives? You can think about the volume of a balloon and temperature. Have you ever stuck a balloon in the freezer? What happens to it? It shrinks. Have you ever heated up a balloon? It gets bigger. You heat it up too much, it's going to pop. So temperature and the volume of the balloon are proportional to each other. You increase one, you increase the other. Maybe, it might not be as simple as just K, but the intuition, that's what we're saying.
To clarify, that happens when pressure is constantly.
No. That's why I said we're kind of being fast and loose.
Oh, okay.
You already know ideal gas law. Trying to think of one that just has just two variables. What's a simple day-to-day thing with just two variables? Okay, the amount of money you have in an investment and the amount of money it makes you, right?
Yeah.
When you think about interest, not percent interest, but the interest you earn on investment, okay, that's proportional to how much money you put in. There you go. So let's say we do keep the investment really, really simple. I say, however much money you'll loan me, I'll pay you back that plus 10% in a year. So I'll give you 10% interest. So if you give me $100, how much money do you make in a year?
Really 10%.
Well, 110, but how much money do you make? You make $10. So the amount you make is proportional to how much you give me by a constant factor, 0.1.
Okay.
So how much you make, y is how much you make, is equal to 0.1 if I'm giving you 10% interest times however much you give me. Proportionally related. Make sense? Okay. So we also have what we call an inverse relation. An inverse relation is of the form y is equal to some constant divided by x. Now they're inversely related. The smaller y gets, the bigger x gets, or the bigger x gets, the smaller y gets. If I divide k by a bigger and bigger number, y gets smaller and smaller. They're inversely related. How nice I am to you is inversely related to how many times you punch me. I don't know. The more you punch me, the less nice I am to you. Okay. So proportional and inversely proportional is, I think, how the author says it. Next, we have power functions. A power function is f of x equal to x to some constant. Some a, where a is a positive number. Oh, no, just a constant. Doesn't matter. So f of x is equal to x to the power of a for some number a. Good? Let's go through some of these real quick. What would the function roughly look like if we make a the power of 0?
1.
It's just a constant function, right? Looks like that. Oops, that's sloping. Then we just get f of x is equal to anything to the power of 0 is just 1, so it's just this 1.
Yeah.
Right? Okay, what about if a is equal to 1?
It'd be identity.
Then we get the identity function. Looks like this, right? What about when a is equal to 2?
Exponential.
No, parabola. We've already done that one. X squared, we've seen this one a couple times. Right? Notice if x is to the power of 2, then it's always a positive number coming out here. With me?
Mm-hmm.
Okay, what about if x is to the power of 3?
Sharper graph.
No.
Let's get a rough idea of what this one looks like. So when I plug in 0, what do I get? 0. 0 cubed is 0, right? When I plug in 1, what do I get? 1. When I plug in negative 1, what do I get?
Negative 1.
Negative 1 comes down here. You see that? Negative 1 times negative 1 times negative 1 is negative 1. When I plug in 2, what do I get? 8, so we're already way up there. And when I plug in negative 2, what do I get?
Negative 8.
Negative 8. Ah, this function sounds odd. Symmetric with the origin. It's an odd function. Its exponent was odd. This is where even and odd functions get their name.
Oh, that doesn't make sense.
Okay, and then a to the 4. Let's try briefly graphing this one. When I plug 0 in for that, so if we have plug in 0 to x to the power 4, so 0 to the power 4 is 0. 1 to the power of 4, that's a massive number. 1. Negative 1 to the power of 4 is even bigger. Still 1. 2 to the power of 4. 16. Yeah, we can't even. Already off the chart. So this is going up absurdly fast, so way steeper parabola. Just shooting way up there. It's not a parabola, it's like a parabola. But way steeper. And that's a to the 4. If we did a to the 5, it's going to look roughly like this shape, but steeper. And a to the 6 is going to look like this, but even steeper. A to the 7 like this, but even steeper. A to the 8, etc. And all the ones where we have even exponents are going to be even, and all the ones where we have odd exponents are going to be odd. Good? Okay, polynomials. Polynomial is any function of the form f of x is equal to a constant times x to some power plus a constant times x to some integer power plus dot 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 dot. So it has this form. All your a's are just constants and your x's are variables. So any function where all your x's are raised to positive integer values is a polynomial function. We call the a's coefficients, and they're the coefficients of the term. So, quick example of a polynomial function. F of x is equal to x to the 4 plus 2x plus 1. Is that a polynomial function?
Yeah.
Yes, that is a polynomial function. Doesn't this mean that we need to have every single term from 1 all the way to n? So don't I have to have an x cubed in here and an x squared?
Sure, the coefficient's just 0.
Yes, the coefficient's just 0. If we want to write it out so it followed the same form, we would have written this as f of x is equal to 1 times x to the 4 plus 0 times x cubed plus 0 times x squared plus 2 times x plus 1. And we could have spelled it out like that. So, still just polynomial. Let's try some more up here. Tell me if they're polynomials. One more thing I should have said. So since the highest power in the polynomial I just erased was 4, then we say that the, what do we call it? The degree of the polynomial is 4. So that was a 4th degree polynomial. N here is the degree of the polynomial. It's your highest value of your exponent. So if n is 4, we just did an example where n was 4 and we add some a's in there. So the degree of the polynomial is just whatever the biggest n is that shows up if you write them in decreasing order. So let's write another one. So f of x is equal to x to the 5 plus pi x minus square root of 2. Is that a polynomial?
Yeah.
I think so. I don't know.
What do we think, Jeremy? We need some tiebreakers in here.
Yes. Doesn't the exponentials have to decrease? Oh, but then they're all by 0.
No.
Too bad. The answer is yes. Okay, so let's make sense of it. So it's a 5th degree polynomial, so n is 5. The a's just have to be any real number. So we could have rewritten this out. I think we can still see this far on the camera. Could have rewritten this out as f of x is equal to 1 times x to the 5 plus 0 times x to the 4 plus 0 times x to the 3 plus 0 times x to the 2 plus pi times x plus negative root 2. So the only thing we require for it to be a polynomial is all our powers of x have to be positive integers, whole numbers, or 0. Well, I guess we didn't include on that, so not 0. So positive integer whole numbers. And all the coefficients of the terms have to be real numbers. 1's a real number, 0's a real number, 0, 0, pi, negative root 2. So all the a's have to be real numbers. And then your n that you start with just has to be some positive integer or 0. Make sense? Let's do another example.
So what is not a polynomial?
Well, let's make sure we know a polynomial before we know not a polynomial. Okay, let's look at another one. F of x is equal to 7.
Yes.
Yes. Wonderful. F of x is equal to the square root of x.
Yes. Well, no.
Your ends have to be whole numbers, don't they?
What do you think, Jeremy?
I'm thinking.
Is it because x can be a negative number, or?
No.
No! Square root of x is x to the 1/2, right?
Yes.
That is not a positive whole, that is not an integer exponent.
Oh.
They have to be integers, exponents.
They have to be in order, maybe.
No, you can change the order. Addition is commutative, so it's still the exact same equation if you change the order. We just typically write them in descending order for convenience. Okay. So, polynomial functions. All the x's are raised to whole number powers with any coefficient you want that's a real number. Add as many of those together as you want, and you have a polynomial.
So most numbers, or most scenarios, we might draw.
We will work with polynomials a lot. So let me write another one. F of x is equal to 5 minus 3 squared times x squared plus 2. Is that a polynomial?
Yep.
Yeah. Can you have multiples of the same one, like multiple x to the power of 2's?
Well, I don't know. Let's look at this one for a second. Let's simplify it. What's 5 minus 3?
2.
2. What's 2 squared?
4.
So this is equal to 4x squared plus 2. Is this a polynomial?
Yes.
Yes.
That's the exact same thing as that. So that's a polynomial.
Yeah, so it is a polynomial.
So it's a polynomial. So yeah, you can have as many x squared terms as you want because at the end of the day, you can collect them all together. So you can still write it this way. Make sense?
So in the end, you should write it that way. That,
Well, should. If it's possible to write it like this, it's polynomial. It's possible to express it this way.
okay.
So if it's equal to this, because you can't express it this way unless it's equal to that. So if it's equal to that, it's polynomial. Make sense?
Yes.
So those are polynomials. Now let's move on to our whiteboard and start talking about, well, let's go ahead and do break and we'll come back and start talking about rational functions. I know we didn't do break last time because we were tight for time, but typically give you a 10 to 15 minute break in the middle. Give you time to go run around the building, get that oxygen flowing, you know. Don't want you falling asleep in class again. It's happened 3 times and we've only had 1 class so far.
It happened once.
Oh, it did happen?
Yeah.
Actually, it's water. So water fountain turn back on, do you guys know?
No idea. Yeah, I just remember.
Nope.
I thought that was some senior pieces to fix those.
What was it?
I thought that was very senior pieces.
Yeah. One half of those being mandatory.
She probably just has to go with the showings.
Also.
Oh, actually, there's something intentional because of COVID.
That's what I thought too.
That makes sense.
Does the academy do anything to kind of policies?
They did last year, not really anymore.
What you doing for your senior thesis? Huh?
I have no idea.
Thought you were fixing gradebook.
I did want to do any type of programming, but I haven't learned enough to know projects like that.
be fitting the whole whiteboard on this. Okay, that should work. So we just finished talking about polynomial functions. Now we're going to move on to rational functions. A rational function, f of x, is equal to the quotient of two functions, p of x over q of x, where p of x and q of x are polynomial functions. So one polynomial function over another polynomial function gives you what we call a rational function. Make sense?
So you take an element from one divided by the other, and that equals rational.
Is this a polynomial function?
Yeah.
Sorry, f of x equals this whole thing. Is this whole thing a polynomial function? No. The whole thing. Top m, this is not a polynomial function. This is a polynomial function, just the top and just the bottom. But altogether, that is not a polynomial function. It is a rational function. Okay. Give you a really quick example of one that's rational but not polynomial that just should have built in intuition. 1 over x. There's a really simple one. This is not polynomial. 1 over x is not polynomial. Because this is the same thing as x to the negative 1. Your exponents here have to be positive whole numbers, or 0. Make sense? But it is a rational function, because it can be the same thing as 1 over x. That's polynomial, it's rational. Rational function. Make sense?
Yep.
Okay, so that's polynomials and rationals. Finally, we have algebraic functions. What's an algebraic function? An algebraic function is almost pretty much any function you could think of writing down without using trig functions based on what you know now. Basically what it is. So what is it? Any function constructed from polynomials and algebraic operations, meaning plus, minus, times, divide, exponentials, etc. Roots is a type of exponent, yeah. So square root for short. So here's a bunch of examples of algebraic functions. Good?
Okay.
Okay. So now we move on to trig functions. Last type of functions we're going to talk, I guess exponential. Let's do exponential really quick, then we'll come back to do trig, because I want to spend a little bit more time on trig. Exponential functions. Now exponential functions, they look a lot like power functions. You just flip where the x and the power are. So notice for a power function, we had f of x is equal to x to the power of some constant. Over here, an exponential function, we have a constant to the power of x. See the difference?
Yep.
Okay. Where a is not negative and it's not equal to 1. If it was equal to 1, then that would just be a constant function. 1 times 1 times 1, no matter how many times, it's just a constant function. So this is an exponential function. Now let's get a rough idea of what these exponential functions look like. Why am I using such a big number? Let's use 2 here, 2 here, 2 and 2. And look at 2 examples of typical exponential functions and one where the x is negative. And let's see what these look like. So, getting a rough idea on how we plot this, what is 2 to the power of 0? 1. So, notice that a to the power of 0 is equal to 1. So it doesn't matter what the a is. For any exponential function, it always goes through the point 0, 1. Doesn't matter what that a is. When you plug a 0 for x, you always get 1 out. So every exponential function goes through the point 0, 1. Go ahead.
If you added a y-intercept to that, is it still an exponential function?
Yes. So you can shift an exponential function up. But when they're these simple exponentials, no other terms, then always goes through 0, 1. Okay, so now what about, what's 2 to the power of 1? 2. So when we plug in 1, we get 2 out. What's 2 to the power of 2?
4.
When we plug in 2, we get 4 out. And when we plug in 3, we get 8. When we plug in 4, we get 16. By the time we plug in 10, we get 1024. Blows up.
Is that called an identity?
No, it's an exponential function. What do you mean identity? Identity means it spits out what you put in.
Yeah. Continue.
Okay. Now let's plug in a negative number. 2 to negative 1 is the same thing as what?
1/2.
1/2. Right? 2 to the negative 1 is the same thing as, remember, how do you get rid of negative exponents? You can make them positive if you put them in the denominator. So, 2 to the 1/2 is the same thing as 1 over 2. Or 2 to the negative 1 is the same thing as 1 over 2, which is 1/2. Right? What happens when I plug in 2 for x, or negative 2 for x?
Get 1/4.
Right, 2 to the negative 2 is the same thing as 1 over 2 squared, is the same thing as 1 over 4, is the same thing as 1/4. If I plug in 10 for x, what do I get? Or negative 10 for x, what do I get?
Yeah, 1 over
1 over 10.
1 over 1024. Teeny, teeny, tiny. Is it possible for me to ever get 0 out of this thing?
Nope.
No.
No. So this thing goes getting smaller, smaller, never actually getting 0, and then shoots off and blows up like that. So it doesn't ever actually reach this line, it just gets closer and closer. Make sense? Now let's look at the negative exponential function. What does the negative do? It just flips around. So it just makes it look like this. Same exact picture, flipped.
Okay.
Make sense?
Yep.
Because now, when we plug in 2 to our function, we get 1/4. And when we plug in negative 2, we get 4.
Makes sense.
Okay, so that's an exponential function. Now, logarithms, I'm sure we'll do a review later where we go over all the log rules. But for now, what do we know about logarithms? They're the inverse functions of exponentials. Right? A log n does an exponential. Do we remember even what a log is?
It's been a while.
All right. So, let's see. Let's write our 2 equations. If I have a to the power of b is equal to c, then when we do log of c equals b. So a log s, let me write actual numbers. So if I'm doing log base 2 of 16, they ask the question, what power do I have to raise 2 to get 16?
4.
4.
Okay.
2 to the power of 4 equals 16. A to the power of b equals c. A to the power of b equals c. It's another way of writing this. But whereas an exponential function, so if we think about this in terms of an exponential function, if I say a to the x equals y, and now I write this as a logarithm, another way of writing that exact same thing is log base a of y equals x. So an exponential takes in an x, spits out a y. A logarithm takes in a y, spits out the x. They undo each other. They're inverse functions.
Okay.
The same way that addition and subtraction are inverses of each other, the same way that multiplication and division are inverses of each other, so too are exponentials and logarithms. Make sense?
Yeah.
Okay. So they're just inverses of each other. So let's try plotting one of these and then see how it comes out.
So logarithm has 2 inputs.
No, a is a constant. Look at this function right here.
No, I understand. I'm just saying if you were to use a log function in your calculator, you'd have 2 inputs.
You specify what log you're using.
Also, log 2 is the
It
same.
has 2 inputs the same way that an exponential has 2 inputs. You specify the same material.
Okay. That makes sense.
Okay. Logs. So let's plot the log function now using what we know about what I just told you. Okay, plug in 0. 2 to the power of what equals 0? 2 to the power of what equals 0?
0.
No.
Nothing. You can't do it. I can't find something 2 to the power of x equals 0. There's no x I can find that gives me a 0. Right? Notice what we said up here. This function never actually reaches 0. Right?
Yeah.
So we can't ever actually take 0. So a log function isn't defined on the entire domain. And its domain is actually going to be 0 to infinity, are numbers that we can take logs of. Can't take logs of 0, you can't take logs of negative numbers. Because similarly, there's no way I can find an x to make that equal something like negative 5. If I can't get to 0, I can't get to negative 5. Make sense? Okay, so now let's try 1. 2 to the power of what equals 1?
0.
0, right?
I have a question. So you said you can't take negative numbers, but what if your base was negative?
What if your base was negative?
Oh, never mind.
And notice we also disqualified that with our exponential function. So we did it with both.
I see.
Okay. So, when we plug 1 into our function, then what did we get?
0.
0. So when we plug in 1, we get 0. So it goes through the point 0, or 1 comma 0. Notice up there, it went through the point 0 comma 1. Here it goes through the point 1 comma 0. With me? Okay, now let's plug in 2. So when I plug 2 into the function, what do I get? 2 to the power of what equals 2?
I don't know.
So now I'm trying to find the x that gives me 2. Well, this is my y.
It would be 1 then.
So I'm plugging in the x here, we're looking for the y that gives me that.
1.
1. So when x is 2, y is 1. What about when x is 4?
Then y is 2.
Then y is 2. So by the time there we get to 4, and that's going to shoot off the chart. So this thing is going to look like this. And get closer and closer to 0, and never actually get all the way to 0. So, notice it's this thing reflected across this line. Or another way to think about it, switch all your x's and y's here, and you get this. They're inverses of each other. Swap all the x's and y's.
Okay.
Make sense?
So
Yeah.
what would you call the process of swapping it down, the process of having the negative x? So is that
Going
mirroring?
from here to here.
Would you call that mirroring?
Well, you could do two things here if you want to call it mirroring. You need to reflect it this way, and then reflect it that way. You need to do two of them. Yeah.
Which you, what would you, oh, okay.
Or you could reflect it across the line y equals x. So if you put a mirror right there, and try and plot its reflection, then it'll be that.
Gotcha.
Make sense?
I wasn't sure if there's a unique word for those two processes.
I don't know, probably. Okay, so now let's go back to our trig functions, since for some of you, you haven't really seen these before, so we're going to focus more on them. So, what does cosine of x give me?
Cosine of x.
What's our definition of
Y.
cosine of x?
The y.
Y.
No, it's the x coordinate on the unit circle.
Oh, the cosine. Sorry.
Your unit circles that we just talked about. How do you find the cosine? What's the cosine of 0 degrees? The cosine of 0 degrees is the x coordinate at 0 degrees,
It'd be 1 then.
which is 1. With me?
Yeah.
So I'm going to start plotting the cosine function. When I plug in 0, so here's my angles I'm plugging into the function, and I'm going to plot cosine, what comes out. So when I plug in 0, when my input is 0, the cosine function spits out 1. So that's right here. When I plug in pi halves, what does it give me? What's the x coordinate at pi halves?
0.
0.
0.
Yeah.
When I plug in pi, what does it give me?
-1.
-1. And just to help get some points in between, when I plug in pi fourths, what does it give me? root 2 over 2, which is somewhere up here. And then over here, I plug in and it gives me negative root 2 over 2. Okay. And we can continue on. What's x at 3 pi halves? 0. That's at the bottom of the circle. The x coordinate at the bottom of the circle. And then what's the x coordinate at 2 pi? 1. And then what's the x coordinate at 3 pi halves? Or at 5 pi halves, I mean? 0. Okay. What's the x coordinate at negative pi halves?
0.
So at the bottom of the circle, we go back pi halves.
Okay.
Yeah, that's right.
Yeah, I see that.
Okay. What's the x coordinate at negative pi? At negative half a circle?
Negative 1.
-1. Okay. And so hopefully you see roughly what this function looks like. This is plotting the cosine. You give me an angle, that spits out the cosine at that angle. With me?
So you carry frequency.
Yes. Has a frequency of 2 pi. That's how long it takes to get back to where it started. Notice the function repeats over and over and over again. We'll take the same pattern over and over again to infinite, however far you want to go. Okay, now let's plot the sine. What's sine of 0 degrees?
0.
Sine of 0 is 0. What's sine of pi halves? 1. What's sine of pi?
0.
0. What's sine of 3 pi halves?
Yeah.
What's sine of 2 pi?
0.
What's sine of 5 pi halves?
1.
And what's sine of negative pi halves? Negative 1. That's right here. And what's sine of negative pi?
0.
0. And so if we try to roughly plot this thing, it would look like this as well. So it looks like the cosine function, but shifted a little bit, right? Notice that they're just out of sync with each other by pi halves. If I could grab the sine function and pull it back pi halves, then they would equal each other. Or if I took the cosine function and pushed it forward pi halves, then they'd equal each other. So this is an identity we showed to you a different way last week, same identity. Cosine of x plus pi halves. Is that right? Or should it be pi halves plus x? Oh, same thing. Pi halves plus x is equal to sine of x. Did I do that right?
Yeah.
Sounds right to me.
I think I did pi halves minus x last time. But we could just check it real quick. So cosine of pi halves, plug in 0 for x, so cosine of pi halves is 0, sine of 0 is 0.
That would work because it just shoves it forward.
Yeah.
Yeah.
So it just shoves it forward. Anyways, so there's plotting those two functions. Good?
So sine is exactly in the center between. Okay. Yeah.
So cosine is an even function, sine is an odd function. Cosine is one that's symmetric, sine is one that comes through like this. Good?
Okay. Is there any reason that would change with trig functions?
Any reason what would change?
Those two. Is that all there is with trig functions?
That's sine and cosine, and then you could plot the rest. Now you can plot tangent with these, cosecant, cotangent. We'll plot the rest in chapter 3. I just wanted to introduce it to you here and have you actually work through plotting them. And we'll reference these plots a lot. Okay. Huh?
Is that okay?
Okay.
I think the identity was x minus pi halves.
X minus pi halves for shifting it back pi halves. So
We only did 1 point. Can we do pi halves to check that? Because in my head they're not adding up.
So sine of, you said pi halves minus x?
We said cosine of pi halves plus x equals sine of x.
Yeah, I think it should also be minus.
I was thinking x minus pi halves, cosine of x minus pi halves,
X minus pi halves.
and cosine of that, or I guess,
Doesn't matter which way you go, right? So plug in, I don't know, let's do 3 pi fourths real quick. So sine of 3 pi, we'll just spell it out so that we all follow the thinking. Minus pi halves is the same thing as cosine of 3 pi fourths let's see if that's true. Sine 3 pi fourths when we subtract, that's going to be sine of pi fourths. Is that equal to cosine of 3 pi fourths?
No,
Cosine of 3 pi fourths, the x coordinate
it's
is negative. So no, that one doesn't work.
So that would shove it forward, but then they would meet, but then they go off.
So that's taking the sine function, shoving it back by pi halves,
Which they would meet on
which
zero.
seems like it should work. All right, let's not get too caught up on this right now. We'll come across those identities again and we'll correct ourselves. But, because we're running out of time. And we still got another section to cover. So, section 1.2. Section 1.2 is about combining functions together. So if I want to add, so if f and g are two functions and I want to add them together, I want to talk about the function f plus g of x. That's the same thing as f of x plus g of x. You probably would have guessed that's exactly how it works. If I want to talk about the difference of two functions, f minus g of x, that's the same thing as f of x minus g of x. Same with multiplying, same with dividing. Make sense?
Yep.
Okay. So let's do a quick table playing with some of these to get a feel for how they work, how they go. So we'll say f of x is equal to the square root of x, g of x is equal to the square root of 1 minus x. Really quick, what's the domain of x? Domain of f, sorry.
0 to
Greater than it's, yeah.
These are all the numbers we can plug in there, right? Now let's look at the domain of g.
Has to be 1 or 1 comma, negative 1 comma 1, right?
You're saying it's this?
Brackets, yeah.
Negative 1 to 1.
Is that right?
Is that right?
no.
What is it? Hold on, let's make sense of why this one doesn't work.
Because if you plug in
Oh,
negative 1.
I did it back.
We can plug in a lot more in this. For example, what do I get if I plug in negative 2?
You
Negative
get
1.
root 3.
Negative negative 2 is 2, plus 1 is 3, root 3, that's perfectly valid. So you're being too restrictive.
Not negatives.
All the numbers you picked work, but you're being too restrictive. What's that?
Infinite negatives?
Infinite negatives. So we can
And
do
then
negative infinity up to 1. Like that, right?
Yep.
Yep.
Okay.
Not clicking? Okay, so notice where do their domains overlap? So if we're talking about the domain of both of them,
0 and 1.
then that is just 0 to 1.
Okay.
So that's one gotcha when you're combining functions together, is the domain is going to be at least this restricted. The way you bring them together might restrict it even more, but it's going to be at least this restricted. Typically. I guess there might be some way that they cancel out. But very typical. So be careful of your domains. Is what we're going to see here. So let's do some of these and see the domain of the function. So f plus g of x, what does it look like?
I didn't get it.
That's going to be square root of x plus square root of 1 minus x. That's it, right?
Yeah.
What's the domain? It's just 0 to 1. Nothing weird?
That's it?
Yeah, that's it.
Okay.
Minus, exactly what you expect. That's just going to be x minus square root of 1 minus x. Domain, exact same thing. Switch the order, doesn't matter. 1 minus x minus square root of x. Notice that those aren't the exact same thing. Those are two different functions, right?
Yeah.
That and that, but the domain, still the exact same domain. Let's look at multiplied. If we have the square root of x times the square root of 1 minus x, well, if we wanted, we could distribute that x in there and then say that this is a square root of x times 1 minus x, which is equal to the square root of x minus x squared, if we want.
But it would still be the same domain, right?
But the domain, is the domain the exact same? I think so. Let's think. We can't let this become negative, so we can't plug in numbers bigger than 1. I think it's the same domain. And we can't let this be negative, so we can't plug in numbers smaller than 0. Okay. So yeah, I think it's the exact same domain. Okay, f over g. Let's look at that one. F over g, that's the same thing as square root of x over square root of x minus 1. What's the domain there?
You can't have it be 1 anymore.
We can't allow it to be 1 anymore. Otherwise, we'd be dividing by 0. You see that?
Yep.
So now the domain here is, we can still plug in 0.
Yeah, I think
So it's
still.
0, 1 not included. Right? And then if we do square root of x minus 1 over square root of x, now what's our domain?
Not including 0 to
Isn't G 1
including.
minus X under the radical?
Did I do those backwards?
Yeah, you did X minus
1 minus x, 1 minus x.
So
Thank you.
now it's the same domain, but
1.
not
Yeah,
including 0.
now that domain makes sense.
Okay, thank you. And then for the next one, what's the domain?
Not including 0.
2, 1, including 1.
Is it 0 to 1, not including 0?
No 0, but include the 1, right?
Yeah.
Okay, so now we're ready for function composition. If f and g are functions, then the composite function, f composed with g, that's not a times, that's an open circle, like a really small o. F composed with g is defined by, f composed with g of x is just f of g of x. You with me? F of g of x. The domain of f composed with g consists of the numbers x in the domain of g, for which g of x is in the domain of f. So looking at that picture I have down there, hopefully this will make sense. So g takes x's and then maps them to some value g of x, right? And then f takes that g of x and maps it to f of g of x.
So you have to solve-
That's what f composed with g of x
so you have
does.
to solve g first.
You don't necessarily have to solve g first. We'll do a quick example of one of these to give you a sense of it. Let's say that we have f of x is equal to, I don't know, x squared, and we'll do g of x is equal to x plus 2. Okay? So let's really quick write out f composed with g of x. Well, that's the same thing as f of g of x, which is equal to f of, what's g of x? X plus 2, which is equal to x plus 2 squared.
Yeah.
Does that make sense?
Yep.
Now, for contrast, really quick, let's also write out g of f of x so that we can see how they're not the same thing. G of f of x is equal to g of f of x is equal to g of x squared is equal to x squared plus 2.
Yeah, makes sense.
So that's just saying that the g of x goes where the x would be in the fx situation.
Yes,
But you have to get the output.
that's
of G.
exactly what it means.
So the output of G you apply to as the input of F.
Yep, take the output of g as the input of f, or the output of f as the input of g.
Yeah. Makes sense.
Okay, so that's function composition. And it's just doing two functions together, plugging one function into the next function. So, guess we'll run through some of the author's examples here. Give you some space on the board. Okay, so he's saying we'll have f of x is equal to square root of x, and we'll have g of x is equal to x plus 1. Now, first thing we're going to find is Oh, sometimes he does with themselves. That's what I asked for. So we'll just go through each of them. Doesn't matter what order we do. So first let's look at f composed with g of x. F composed with g of x, what's that going to equal? That's going to be f of g of x, which is equal to, hopefully you can just see it all in one go here now, the square root of x plus 1. You see all that in one go?
Mm-hmm. Yeah.
Yeah.
Yeah? Okay, so let's notice some things real quick about domains here. What's the domain of this function?
0 to infinity.
0 to infinity. What's the domain of this function?
Any number.
Everything. And what's the domain of this function?
0 to negative 1 to infinity.
This one is negative 1 to infinity. So, the rule is that the domain after the composition has to be a subset of the domain of the first function we solved for, of the most inner function, of g, of the first one. Remember, f composed with g, we do g and then f. So this has to be a subset of this, which it is. So we're good. Let's look at the next one. So this time we're doing g composed with f of x. Now this time we're doing g of f of x. And now this is going to be equal to the square root of x plus 1.
So it doesn't have to be a subset of both, is what you're saying. Meaning the subset of f and the subset of g doesn't need to be a subset of both.
Right. So it's important to note that this thing is larger than that thing.
Yeah.
Right. So this had to be a subset of that, but now notice what's the domain of this thing?
Just 0 to infinity.
0 to infinity, which you'll notice is a subset of that because they're the exact same thing. Okay? Okay, let's look at another one. The other two the author does is f composed with f of x. What does that equal?
F of x.
F of x. And what does that equal?
Square root of x.
The square root of the square root of x. Sure.
Which is x to the 1/4.
X to the 1/4.
I have a question.
Absolute value of x to 1/4, if you want to write it that way.
Right. When you said that the domain of the composite function has to be a subset of the domain of the inner function, are you saying that for any composite function, or is there?
For any. Because remember, if you think about how we did it in discrete math, you map it through one function, then the next. You have to start by mapping through the first. And you can only map the first function's domain through the first.
Right.
So that's your natural restriction. And once again, this is still just 0 to infinity, right? Because if you look at the inner square root, we can plug in anything but negative numbers, and it will spit out non-negative numbers, so we can take the square root again. So nothing changed there. Now let's look at g composed with g of f of x. G composed with g of x. What's that equal to?
G of x.
Okay, I'll do that. G of x, and then what's that equal to? Give it to me all in one go.
X plus 2.
X plus 2, right? X plus 1, x plus 2.
Makes sense.
Good? All right, domain of that, all real numbers. Same thing as the initial function. Okay.
They didn't do more than just 2 functions.
Yes.
And you can.
Yep, you can compose as many things together as you want. Okay, now we're going to talk about vertical and horizontal shifting. So vertical shifting. Y equals f of x plus some constant k shifts the function up or down, however much the k is.
Yep.
Make sense?
Yep.
Okay. Y equals f of x plus k, like that, shifts the function left or right depending on the k.
Yeah.
And if k is negative, it's shifts it right.
Let's see. So when you add a k to it, then if k is positive, let's think, k shifts it left. Adding a positive number shifts it left. Smaller number gets you what it used to before. So let's imagine that k is 2. So what f of 1 used to be, so now f of 3 is equal to f of 1 plus 2. So what you had to use 3 to get, you now get it 1. So it shifts it to the left too. Subtracting shifts it to the right.
Okay.
Let's plot one of these real quick just to see it.
Yeah.
So let's do really quick y equals, well, we'll say f of x. F of x is equal to x squared, one that we're very familiar with, right? So now let's look at f. Should we do positive or negative? Maybe the negative's less intuitive, so we'll do the negative. Okay? So I'm saying that this should shift it to the right 2 units. With me? When we plug this in, this is x minus 2 squared. That's what we're plotting here, right? So let's really quick plot it. Da-da-da-da. Plug in 0, what do we get?
For f of x or f of x?
Sorry, for this function. We're plotting this function now. We know what this one looks like, right? It's just a parabola right down the center, nice symmetric. So when I plug in 0, what do I get? 4. So when I plug in 0, I get 1, 2, 3, 4. When I plug in 1, what do I get? 1. Is everyone following what we're doing?
No.
Okay, sorry. We're plugging into this function right here, this function. We're plugging in for x minus 2 squared.
Okay.
When I plug 0 into that, what do I get?
You get 4.
4.
4. When I plug 1 into that, what do I get? 1 minus 2 is negative 1. Negative 1 times negative 1 is 1.
Yeah.
Okay, you with me?
Yes.
When I plug in 2, what do I get?
0.
0, right? When I plug in 3, what do I get?
1.
And when I plug in 4, what do I get?
4.
So now it looks like this.
Which is offset by 2.
So it took our parabola that we had. So if we just did x squared, that's a parabola right down the center. Try and throw it on here really quickly. So just x squared looks like this. But now if we do x minus 2 squared, it shifts it to the right 2 units. Good? Okay, so subtracting shifts it to the right. Adding shifts it to the left. If we would have switched this to a plus 2, that would have shifted it over here, and we would have gotten the exact same thing.
Yeah.
Okay.
With me? And I think the vertical one's way more obvious how that shifts up and down, right?
Yeah.
So it's just plugging it in. That it's a little weird that that's how it works, but that's how it works. So that's shifting the function. And then we have scaling the function. And that's the last thing we have in this section. So, try and just get the author's table written up here real quick. And we'll make sense out of it this one. So, here's this table. For c greater than 1, if we make our function y equals c times f of x, we'll see what that does. Y equals 1 over c times f of x. Y equals f of c of x. Y equals f of x divided by c. And then we have for c equal to negative 1, I don't know why we specify that. Two special cases where we ignore the c now. We're going to look at y equals negative f of x and y equals f of negative x. And see what all these do. Okay, so we want to get intuition for what these things do to a function in general. So if I take a function and I multiply it by a bigger number, what does that do?
Makes it bigger.
It stretches it vertically. It makes your y's jump up faster, so it stretches your function vertically.
Okay.
So if f of 1 used to give you 1, now if c is 2, f of 1 now gives you 2.
Okay.
Yeah, I see that.
So if c is 100, if f of 1 used to give you 1, now f of 1 gives you 100. Stretches it vertically. Because c is a number bigger than 1.
When you, for that top one, you're scaling it by c from the origin.
From the origin.
Okay.
Yes. Next one, 1 over c does the inverse of that. It compresses it.
Makes sense.
Makes it flatter. So if we were doing our parabola and we were flattening it out, so if we had c was 16 here, then when we plugged in 4, rather than getting 16, we'd get 4 goes now to just 1. So it would grow very slowly at first,
Yeah.
right? So that compresses it. F of c of x, this one compresses it vertically. So this stretched it, sorry, not vertically, horizontally. This stretched it vertically, this one compressed it vertically. Similarly, this one stretches it, oh sorry, this one compresses it vertically, and this one I keep saying the wrong words. Don't let me say the wrong words. These two are horizontal, these two are vertical. Okay, I've got those words out there.
Yeah.
Stretch, vertical. Compress, vertical. Compress, horizontal. Stretch, horizontal. I think I got that right. That's what appeals to my intuition.
That sounds right to me.
Yes, compress and stretch. So this compresses, this one stretches. So maybe we'll come back and do like one like this or one like this, one of those to help that one make intuition, but these two I think will already make intuition to you. What these ones do. If I take f of x and I suddenly make it negative, what does that do? If I make my whole function negative,
It flips it.
it flips it across the x-axis, right?
Yep.
So everything that was positive is now negative, everything that was negative is now positive. Similarly, if I switch the inside from x to negative x, what does that do?
Mirrors it. Flips
That-
it. The y along the
Sure.
y-axis.
Y-axis.
Yes, so
Side.
this reflects it across the x-axis, this reflects across the y-axis.
Yeah.
Good?
Okay.
That's really cool.
So those two, we already have some intuition for, so now we just need to focus on making these ones make sense, right?
Mhm.
You're saying that bottom one reflects across the x-axis, or the y-axis?
This one reflects across the y, this one across the x.
Okay.
Go ahead.
What's the difference between compressing horizontally and stretching vertically?
What's the difference between compressing horizontally and stretching vertically? Give you a quick example. We'll use a sine function. So let's start out with, here's my sine function. Good.
Yeah.
Now I'm going to do the sine function where I do which one first?
Compress horizontally.
If we compress this horizontally, now it looks like this. And then what else?
Stretch vertically.
Stretch vertically. If I stretch vertically, that one would look like,
Just really
I'll just
tall.
draw just over it.
Okay.
So different things. Good? Okay, so let's do one example where we see, I don't care which one of those we do. What do you want to see? You want to see the c in the numerator or the denominator?
Denominator.
I think two people said exactly opposite things. We'll write it over here again. So we'll stick with just our x squared function since we have good intuition for it. So I'll do f of x is equal to, we'll plot x squared, and then maybe I'll say g of x, we'll also plot this one. G of x, we'll say it's equal to what?
3x squared.
We'll say it's equal to f of, you say 3x. which is going to be 3x squared. Let's keep it at 2. I think those will work nicer. So we can.
You change the other three to two?
Oh, thank you. Yeah, so let's keep it at 2. Okay, so let's see what this does. Now, which is it going to do? Compress horizontally. So rather than seeing a typical parabola, it's going to be like a squish parabola, a real narrow parabola is what we're expecting, right? Mm-hmm. Now let's see if we actually get that. So let's plot. Here we are. 1, 2, 3. 1, 2, 3. 1, 2, 3, 4, 5, 6. We're going to be way off the charts here. Should have thought better about that. Oh well. Regular parabola, we know what that looks like roughly. 1, 0, that point 2 goes to 4, and negative 2 goes to 4. Looks roughly like this one, right?
Yep.
Yeah.
That's regular. Here's f. Now let's plot what g looks like, which is f of 2x. Okay, when we plug in 0, what do we get? 0, that's good. When we plug in 1, what do we get? We get 4 already, right?
Yep.
When we plug in 1/2, what do we get? 1. When we plug in negative 1/2, what do we get? Am I losing anyone in this?
No.
We're just plugging in right here.
Yeah.
Okay. When I plug in negative 1, what do we get? 2 times negative 1 is negative 2 squared is 4. So when I plug in negative 1, I get 4. And if we finish, it's going to continue like that. And it compressed it. Right? So here's g. Let's really quick make one more function. We'll call it h. We'll say h of x is equal to f of 1/2 x, just to see it the other way, which is equal to 1/2 x squared. Okay, so now we're going to plot h. Understand what we're doing?
Yep.
Okay, when I plug in 0, what do I get?
0.
0. When I plug in 2, what do I get?
1.
1. When I plug in 4, what do I get?
4.
4. So you see how this one's curving off this way, right? And it's stretched out, and obviously this one will curve off the same way that way. And this was h. So h was stretching it horizontally, and g was compressing it horizontally. So hopefully those now make sense to your intuition. Good?
Mm-hmm.
Okay, that finishes section 1.2. So that's all the material we had to cover for today. So you can use the rest of class to start working on homework.
So,
And ask me any questions you have about homework.
so if you were to stretch it in both ways, you would times it and divide it by the same value.
If I both stretch and compress it the same
No,
amount,
not compressed. What's the other one?
well, these undo each other. One stretches, one compresses horizontally, and up there we stretch and compress vertically.
Oh, gotcha. So, okay, so if you times the function by the same value and then divide it by the same value, it should scale perfect in both directions or something like that.
Oh, I see what you're saying. You're saying if we multiply the function by a constant and then divide it on the inside,
Yeah.
yes, then you
Same
could scale up
value.
the function.
It would scale it perfectly.
Yes, you can perfectly scale up and scale down the function. I don't think we need the recording anymore. So I can start this going.